We are going to talk about functional thinking. And we're going to talk about functional thinking by way of implementing a problem. A lot of times, solutions don't come so easily. We have to reframe our thinking sometimes to be able to find solutions. So, and sometimes we get so convinced ourselves that what we are going to do has to be done imperatively in this example, or it's not possible to do. But it's important to really ask the question, what are some of the ways in which we can maybe achieve that? And one such problem that intrigued me is a problem I got introduced to several years ago. It's a very simple problem, or so it appears to be when you start it. And then when you start looking at it, it seems to get more and more complex, and it can become very intimidating. What I want you to do is, I want to hear a lot of noise in this room, especially if you're sitting alone. Move close to somebody else so you can make noise talking to them. And what I want you to do is, we're going to take a problem, and I want you to turn around and face. You can turn to the person behind you, front of you, to the side, and you're going to spend a few minutes thinking about how to solve this problem. The goal is not for you to find an answer, but the goal is for you to find different options to think about. And then we'll look at a solution, and then I'll give you a little bit opportunity one more time to make such noise. And then we'll look at a solution again. And so what is the problem we're going to talk about? The problem we're going to talk about is what is called, let me see if I have a connection here. It looks like I do. It's called the Conway's. He passed away actually not a few months ago, or within a year, which is sad to hear this. But this is a game he defined. What you have is a universe, and on the universe, I'm going to describe the game in the next few minutes so that you don't have to look it up. So the game is essentially where you have a universe, and the universe is infinite. There are no bounds to the universe, right? And then there are cells in the universe. So in your mind, if you're thinking a universe is an infinite grid, that's great. And so this is an infinite grid of cells. A cell may be alive, or a cell may be dead. So that's the two states of a cell, right? Dead or alive. And if a cell is dead, there are rules for it to come to life. If a cell is alive, there are rules for it to die, and vice versa, right? So what are the rules then? Here's a very easy way to remember. If there is underpopulation, a cell will die because there's not enough social activity, right? It becomes lonely and it dies. And the underpopulation is if there is fewer than two live neighbors. So if there is no live neighbors, the cell dies. If there is only one live neighbor, it dies, right? It keeps talking the same thing over, gets bored and dies. So it needs at least two live neighbors to continue to live. If there are three live neighbors, it lives. So 2, 3, good. 4 live neighbors, that's overcrowding. It doesn't get enough food, it dies. So less than 2 dies, more than 3 dies. So far so good. That's about a live cell. What about a dead cell? There's no life here. What happens? For a cell to come to life, it needs 3 live neighbors. Very easy to remember. Needs a mom, needs a dad, needs a midwife, right? So 3 things, it comes to life. So that's your rule. Question, how are we going to build this game? The rules we're going to follow eventually is that we want to write the code with no mutability, meaning completely immutable. We want to use functional style of programming to build it. So I'm going to give you about 5 minutes. Talk to persons next to you. Don't try to solve the entire problem. Solve only one problem. That is, how are we going to design and implement life and death of a cell? A cell lives if there are 2 or 3 live neighbors. A cell comes to life if there are 3 live neighbors. Otherwise, it's dead. So 5 minutes, think about it. Talk about it. Make noise. All right. So, once again, what we are solving is just a small part of the problem, right? We want to know how to design a cell coming to life or a cell dying. Any thoughts? How can we model it? We're going to class, what does the class do? Yeah, fire away, please.
It will be considered as a dead cell. Something along these lines we can do.
Good first step. Very good first step. Now remember, you always want to think about pros and cons. What's good about it? Looks like there's a good, nice solution. We got a cell, correct me if I'm wrong, we got a cell, we got the neighbors. So based on the x and y coordinate, we can know whether it's a neighbor or not. So given a cell, we can find all the neighbors, see which is alive, which is dead, and we can make a decision. Now, good thought. One of the things I always do is I consider solutions like that, and then I'll ask the question, can this be simpler? Are there things I can get rid of right now and bring in later on when I need to look at it? So anyone else who had similar thoughts to what the gentleman suggested? One other person in the room. 2 people. Anybody else? That's it? Only 2 people? And then I want to know what else people are thinking. Another thought. What was the next one? Who wants to go? Yes, please.
And then we were thinking about how you're going to do how do you calculate for the next generation?
Yeah, so now notice, thank you. This is a little bit of a differing thought, and again, correct me if I'm wrong. What we are saying here is, I don't care about the neighbors. Notice the word he used. I want to know the count of the neighbors. I'm going to twist his words a little bit. Count of the number of live neighbors. We postponed some problem right now. We said, I don't need to know all those details, right? It's kind of like in our lives, we do things very differently, right? For example, I'm thirsty and I'm going to drink this water. And I'm not trying to be insensitive when I say this. Somehow, magically, this water was there and I'm using it. Who put it here? Who bottled it? Who sold it? In Java, what do you call that? Factory. You just ask the factory, can I have an object, please? And the factory says, here you go. How does the factory work? You say, encapsulated, abstracted, I don't care. Bring that idea down. You're saying, I don't know how I will get this count of the neighbors, but somehow it's given to me. Then I can make my decisions with it. Bingo. Let's work on that then, right? So it distills, removes complexity, at least postpones it. So notice what I'm doing here. I'm going to have a next state function. Here's a dead or an alive. I don't want to say Boolean true or false because it's not expressive. What is worse than Boolean true or false? 0 or 1, right? Even worse, some other cryptic things. Those are called cognitive load. Cognitive load is every time you look at it, what does this map to in the domain? What does domain-driven design say? Keep your model close to the domain. The domain expert doesn't say true or false. The domain expert says dead or alive. So what should it be? Dead or alive. Not a Boolean, not a 0 or 1. That's the very first step. Enums, records can be really useful. So in this case, what I'm going to do is to first of all create a cell state. We'll come to the cell in a little bit. Create a cell state, and I'm going to have a next state, dead. So this says for a next state, if it is dead and there are 0 live neighbors, it is dead. If it is dead and 1 live neighbor, it's dead. Dead and 2 live neighbors is dead. Dead and 5, dead. Dead and 3 comes to life. Make sense? So then similarly, the test for live cell neighbor says it's alive, but it is starving to death. It doesn't have enough underpopulation. This is underpopulation. This is right population. This is overpopulation. This is right population. With me? So now what do? I'm going to provide a function called next state. So here I'm writing a code in Java. You can write code in any language you want to. So I'm going to say public static game state which is what I'm calling right here, isn't it? We call it a cell state, rather, pardon me, cell state. So I'm going to say here is a enum called a cell state. It contains a dead and an alive, or the two states it contains. And the game state, next state, and what does it take as an argument? It says I'm going to take a cell state, which is the current state, right? And it also takes a number of live neighbors. And what am I going to do here in this particular case? This is the cell state, pardon me. So what are we going to do here? We are saying, hey, look, if the number of live neighbors is equal to 3, then simply return alive. On the other hand, right? On the other hand, if the number of live neighbors is equal to 2 and current state is equal to alive, then it is going to be returned alive because it stays alive. Otherwise, return dead. Well, is that going to work? Let's find out. So we can go back here. We can run those tests and see if the tests are happy with us. If not, we'll fix it. It says, I don't know what a variable dead is. Oh, darn it. So, pardon me. So in this case, it gives us an error right there because we did not do an import on it. Let's fix that. So that's going to be the dead. And so this is going to be the dead state. Go back and run the test again, see if the test is passing. And the test is happy and passing. So that tells us this was good. Once tests pass, I'm not suggesting you do this or that, but these are the options, right? You can leave it at this if you want to, nothing wrong with it. Or you can use a Java switch expression if you want to. Or you can say return if the number of live neighbors is equal to 3 or number of live neighbors is equal to 2 and current state is equal to alive, then I want to return an alive. Otherwise, I want to return a dead. So you can try different combinations and talk to your colleagues and say, which one do you like? Which one is more expressive? And you can figure it out. Or you can write a switch, like I said, right? So or a switch expression, and so on. So this models, pardon me, that core functionality. Does this? We went from complexity, but that's not as complex anymore, right? When we work on it. And let's be honest about it. If I tell you that I sat down and I came up with this idea in 5 minutes, what would you tell me? You'll tell me, Venkat, you have divine presence? Or you're a liar? Which would be more likely? Divine presence, of course. No, just kidding, right? So, of course, that would be false, right? So, this is not what I arrived just by sitting and thinking. It came after starting with the solutions we talked about and a few other solutions, refactoring, retrying, talking to friends, and then you're like, wait, but why are we doing all of this? And then suddenly we find simple solutions, right? So that's okay, evolve towards it. Good, so we still have one problem. How do you know how many neighbors you have? That is, we just kick the can down the road, right? But the can is still there. You got to either pick it and throw it in the trash or do something else with it, recycle it, right? So what do? How do you know the number of live neighbors? Well, we can say, given a grid, given a cell, go find the number of live neighbors. There's only one problem, right? What's that? Infinite. You cannot store infinity. Next 5 minutes. Give it a try. Where do we go from here? Let's make some noise. All right. So, what are the thoughts? How do we proceed with this infinite universe and finding the neighbors? Because we need to know how many live neighbors are there to feed this computation, right? Yep, please.
First thing is like what is the start point for this thing? So there we localize it like whether
let we'll ask the user like where is the start point.
Yep.
Second thing is like how to store that much data. So again, like storing the infinite data is not an option, but if you localize the data, say you cannot store the population of Earth, you cannot store the population of Bangalore, but you can store the what is the population of Marathalli. So localize that data. Just concentrate on that data, like whether we have something there, and if something comes, we can extract like what is the location point for
So
it.
we said the given problem is infinite, but don't worry about it. Let's just worry about a small grid.
Correct.
So the user says, user, I don't care about what you want. I'm going to tell you that I'm going to give you what I want to give you.
No, no. There exactly, my logic is like user will give me something.
No, but the point is the universe is infinite. If you take a grid, are you going to have infinite of those grids?
But still, like if we have a
The red light goes off to say it's not.
it's a
I
red
like
flag.
such systems, right? Wouldn't that be cool to have in the office? We're thinking about things and light goes off. It's like, now change your thinking. Good try, though. Yes, please.
You have a hash map, and which point? Sorry.
It's still on.
So a hash map that maps a coordinate to the state of the cell, and so you keep track of only the alive cells. So you're minimizing your space.
Bingo. We can turn off that light now. So now let's rephrase your statement just a little bit. And again, don't want to feed words into your mouth. Let me know if this lines up with what you're thinking. The infinite is universe, but life on it is sparse. Right? If the life is sparse, maybe I will only store the live cells. And in that case, it doesn't even have to be a hash map, just can be a set or a list, right? So then we find a way to store an infinite universe. Again, the assumption here is that the life is sparse. And maybe life is sparse and even finite to store it. Maybe a large value, but still finite to store it. And that's still an assumption, right? But we can work with that assumption. So that takes us one step forward. Then the question is, you have a list or a set or a hash map, then how do you, thank you, and how do you find the neighbors of a cell then? I love this. Can I take this home? This is great to have. Yes, please. Never trust a sentence that has the word simple in it. So, how do we find the neighbors? Yes? Our universe is infinite, would you agree?
Yeah. No. Yeah. Like.
Ignoring population of India, life is finite on planet Earth. Don't use the word simple math, because there's no such thing as simple math.
So your x coordinate and y coordinate, so you have these combinations.
But we can't, because we don't have a coordinate system to rely upon, because we got all these cells.
That's what I'm saying. So you have a data structure to represent a point in space. That's what you use as a key for your hash table.
But there are infinite points in space. You're falling into the trap one more time.
We only need to keep track of the ones that are alive.
Not entirely true.
In the beginning.
No, but
as your state evolves.
No, but there's no state to evolve. The problem
everything else is dead. In the beginning, in your initial state, you only keep track of alive.
Agreed.
Everything else is dead.
But how do you know what is going to come to life?
That's what. So you look at the neighbors. They are depending on the state of your initial conditions. You will figure out what the number of live neighbors are. So
here's a live cell.
But you also have to process those neighbors also, which are dead to begin with. They don't exist in your list set hash table, but you process them as well. You know what their neighbor count are, and then again you will change them.
So here we are. Irrespective of the word that we use the word simple, are we simple or complex? This is why it's important not to use the word simple in conversations, because our brain disagrees to see complexities that evolve. Words are very important. Because you're telling the other person, I don't want you to challenge me. I don't want you to think, because this is simple. I've analyzed it. Here's the result for you. Remove those words from your conversation. Here's an idea. Challenge me if it's okay. Here's a simple solution. Hey, I've determined that it's simple. You can't disagree. If you don't understand my simplicity, right? Well, the problem with that solution is, again, pros and cons, right? There's no right answer. The problem with the solution is, when you have a live cell, every single neighbor has to be evaluated. But the neighbor may or may not be alive based on its own neighbors. Right?
Right. So that's very important. Why we need immutable data structures. So in the scan, when you're scanning everything,
This has not yet to do with immutability. It's
no,
complexity.
because you cannot change their state
We're
during
not,
the scan
we're not
process.
concerned about changing their state at all.
Right.
Here is a live cell.
So during the process, when you're evaluating, their states are determined.
The mind blinds you. That's what I'm saying. Here is a cell, there's a dead cell next to it. How do I know that dead cell is going to be alive or not?
No, we don't need to care about what its next state is. We only need to care about what its current state is and make the decision
I
based
know
on
the
that.
current state already. It is dead. The problem is, I want to know the number of live neighbors to determine whether a cell will become alive or dead.
Yes, so we process its neighbors.
Okay, I'm going to move on. So essentially, when you have live cells alone, you want to know the next state of what is going to be alive and what's going to be dead. The problem is, you just cannot process live cells alone to determine this. Because if you process a live cell, well, that cell may be alive or dead. But the question is, what else is going to be alive which is currently dead? So if we go that route, we have to take a cell, then we say, oh, look at the cell next to it, but that one will be alive or dead based on its own neighbors. Now we have to keep computing these things. Will it work? Sure, a lot of things will work. But let's rethink about this. What if we reframe our thinking? What if, rather than thinking about this as cell and code and neighbors, just imagine these cells are really what they are, living and breathing. And what does a cell do? If a cell is alive, it generates heat. There is things around that, you're sitting next to somebody, right? There's a warmthness that, I hope it's warmthness, not cold, right? That you feel. What if cells radiate their heat to their neighbors? If they are live cells radiate, dead cells don't. Well, that's great. We already have live cells. When you radiate these from the cells, now you can simply capture just these signals. You have a collection of signals. So now you're talking about a transformation, right? You're transforming from a list of live cells to a list of radiations or signals, so to use a better word, that you can have. Okay, so now I have list of signals. How is the list of signals useful? So the signals are pointed at a cell, isn't it? So if you have a cell, it generates 8 signals, 1 per neighbor. If you have a cell over here, it generates 8 signals, which means that cell is going to get 2 signals at least in this example. If there is another cell up here that's alive, it's going to get 3 signals. When you have a list of signals, you can group the list of signals for every cell. That's the next transformation, right? So now I can give you a grouping of cells and the number of signals it receives. Now that becomes the number of live neighbors, after all, that every cell has. So we don't need to be looping around for a cell to determine it. Instead, we can just apply a series of transformations. Once we know how many live cells we have, we can then apply that information to this function that we wrote, and we can determine if a dead cell or a live cell evolves into dead or alive. Now, there's no mutability here because we're simply transforming every single step of the data. And to his point, if you're mutating it, which is when this comes in, what do you do now? If you mutate it, you're in trouble. Because by the time you come back to compute it, well, is this the previous state or the current state? Well, this one is a previous state, that one is a current state. That's a mess to deal with. But we don't even have that problem in here when we apply Caesar transformations. But before I go that route, just one small note, not related to this problem. I'm a big fan of code coverage, and I mentioned this in other talks. If I run the code coverage for this code, what are you going to see for what we have written so far? Will the next state be 100% covered? Yeah, it's not a lot of code, and we wrote the test for it. But guess what your code coverage is going to tell you? What was that? There's no problem with brand coverage because there's not a whole lot of code in next state. Next state is fine. Your code coverage is going to tell you you haven't covered the constructor of this class because we never created an object of this class. 3 answers. Look the other way. Don't worry about it. Every time you look at the coverage, you say, that's okay. Yeah, you're laughing, right? Not a good solution. I mean, sometimes people say, look at these test cases, these are okay to fail. I'm like, what does that even mean? Look at the coverage, these are okay to be not covered. Now we got to sit there and keep comparing it, right? Anyone for the first option? No. Option 2, write a stupid test where you create an object and you look at this and say, why are you creating this test? Oh, because the stupid coverage is complaining and Venkat is stupid, he's complaining, so I wrote this test. Anyone likes that option? We have done it. Don't assert, yeah, and it's even worse, right? Can we have somebody to walk him out of the room, please? Yeah, I mean, what? I mean, that's even worse. Assert not null. I just got up and cried. I'm like, why? So you don't like the 2 solutions, right? So there's got to be another solution. So when you run into situations like that, you ask the question, what am I doing? Well, I don't need this object. If you need this object, don't make it an object. Mark it an interface. So if you make it an interface, nobody creates an object of an interface, right? So your code coverage is no longer going to complain. So you don't have to ignore it. You don't have to write stupid test, and off you go. So little techniques like this can be really useful. When you look at a problem, you ask the question, how do I solve it in a sensible way? And not just saying, I'm going to avoid it or I'm going to do something stupid to handle it. You can do something like that. Anyway, back to the problem we talked about. So what we are going to do here is the next step. So I'm going to say a cell generates 8 signals. And again, there's many ways you can probably improve this, but I'm going to start with this. So a cell generates 8 signals, right? So what does that mean? If you give me a cell, it generates 8 signals around it, right? That's what we're going to do. And here's what I'm going to need your help. I need to create a cell, first of all. So I'm going to provide a cell right there. So what is the cell? I'm going to say a record cell contains an X and a Y as a coordinate. And I'm going to provide a public static cell which takes an X and a Y and simply returns new cell with an X and a Y. So that's my cell record. If you want, you can create it as a class, then you're going to write all these getters and setters and equals and everything, but why not simply use what's in the language, right? So it's a record. So then, going back here, we have a cell, and we are calling the cell, and I have a generate cell for signal for a cell. So this says, given a cell 2 and 3, generate these cells, right? So generate a cell for 1, 2, 1, 3, those are the signals. So given the middle one, it sends 8 signals, right? So that's a generate signal for 8 cells. So that's going to take a cell as an argument. So I go back here, and I'm going to say this is public. This is going to be a list of cell and generate cell, and this is going to be a cell we are going to provide. So what am I going to do within the function right now? Within the function, I'm going to say, I want to return all the 8 cells for this cell, right? So how do we return all the 8 cells? Pardon me, this is going to be a static function again. So how are we going to return the 8 cells for this cell? So we could say return cell, and we're going to take the x and y. So here's something you could do. You could say something like int stream.range closed, and you can go from cell.x minus 1 to cell.x plus 1. So that becomes your x range. And then what do you want to do? You could say dot, you can do a map, isn't it? And you can say this is your row coordinate. And then you can say int stream dot range closed, and this is going to be, pardon me, range closed, and this is going to be your y coordinate, right? Minus 1 and cell dot y plus 1. So that's going to be the values, but this is a transformation that itself creates a collection. What should I do instead of map? That's right, flat map, right? You could do a flat map, for example. So then what you can do is you can do a filter on it, and given a value, and maybe I would do this even before this, right? Pardon me. I would do a filter, and I can say here's a column I'm getting, and what am I not interested in? I don't want, if row is equal to cell.x and column is equal to cell.y, and I don't want that, right? So we could say it is not of this. So give me all those that don't meet that criteria. So you're just ignoring the middle cell. And once you do, you got all those cells that you are getting back with the x and y, in this particular case, that you are getting these columns and row. So what's the next step here? So you can then say from this one, I want to return, this is a column you have, right? Is that correct? So you have the cells coming in on this one. Let's make sure we got this in the filter. That's correct. So here we are in the map, and I say here comes the column. And what am I going to do with this column? We'll do a map to obj, and this is going to be returning a new cell with a row and a column, right? Because those are the signals that we want to send from here. And I'm going to do just a static import of it, if I can. And so we're going to get that. I think I messed up here. So this should be a parenthesis here, not here. And this should be end of this one for the filter. That's the flat map. I'm going to continue with that and provide it. So anyway, I'm getting into trouble with these parentheses, but you get the point, right? So you can do the transformation of the cells by bringing in the signals that you can generate. Or you can write it imperative in this case, but you're basically generating a new set of cells. That's what you're doing. Make sense? So this gives you the 8 cells that we are interested in bringing in. That's all we are doing right now. Okay, so can you help me to fix the error here? So we are doing a flat map on this one. We're filtering out the row, and in this case, the row and column, we're saying it's not equal to the row and the cell, right? And then once we get through that, we're doing the filter on it. Once we do the filter, we do the map to object. And once we do the map to object, that gives us the cells. And once we get the cells through that, we want to finish up the flat map at this point and return the result from it. Let's see what it's complaining about. Most likely, it's a stream to a provided an int stream. That's what it's complaining about. So, but the map to object should have helped it. Let's see why it's not happy with me. So in the flat map, I get a row, and I'm saying int stream dot range closed. You have a cell y and a cell 2 plus 1. And what's happening then? I don't know where that error is coming from. Let's pay attention to this. Uh, that didn't go really well at all. And oh, so provides a stream, got it. And finally, what do I need to do? A dot to list, right? Yeah, to list. So let's see if the test is passing and see if that works. So all we did right now is we created the collection of those cells, right? That's what we did. Obviously, you need to write more tests, right? Don't write one test and walk away, right? You need to write more tests. What's the next step after this? Generate signals for a cell which is empty, but this says an empty list of cells generate an empty signal. But this generates signal for all the cells given. So we know to go from one cell to the 8 neighbors. But what if you give me a collection of these cells? Then I need a collection of these signals, right? So can you help me create that? We're going to take one step at a time, right? So generate signals for cells. What's the result of this? The result of this is going to be a list of cell, right? And generate signal is going to be a list of cell. These are cells. And what should the result of this be? Return list of empty, right? Because if you don't have any cells, I'm going to return nothing for you. So if I run this test, it simply says the list is empty. What if you give me one cell, right? What if you just give me one cell? So in this case, I only give you a 4 and 5 in the list of cells. Then it only is going to contain those 8 cells, right? But we can then leap to the next level in here. So I'm going to say, hey, all right, tell me what I should do. I have a collection of cells. I need to send a collection of signals. What am I going to do? What function comes to mind? Map? Or maybe something more than a map. Every cell has many signals. Every cell has many signals. But given a collection of cells, I want a collection of signals. We need to connect this as a flat map problem because it's a one-to-many mapping, right? So cells.stream flat map, given a cell, what are we going to do? Generate signal for a cell, that cell, and then to list. So it's literally a flat map problem because you go from one to many. So that's a many collection of cells, many collection of signals. So it's a very straightforward flat map problem. And that is the challenge, right? A lot of times we know to take a function and use it. But we need to be able to find functions to use. That's when the real absorption happens, right? We need to recognize this as a one-to-many function. And when you see this as a one-to-many function, you say, aha, I need to then apply a flat map. We're making good progress, though. So what are we going to do next? We know to go from one to many. What about many to many? So notice now, what are we doing? Sending 2 cells. Hey, that shouldn't be a problem, right? Because it can work with 1 cell, it can work with 2 cells. And again, once more, more tests. Just don't walk away by writing a couple of tests, right? Make sure it's really working. So we got signals coming in. Here's your next challenge to make this work. So empty, counting, right? Finally, we have to count it. Count for empty signals. If you don't give me any signals, I'm going to give you an empty map. I don't have anything to give you at this point. That is count signals. So how do we implement it? Public static map of cell comma integer. With me? Given every live cell, is it live cell? No, given every cell, pardon me, not live cell. Given every cell, give me the number of neighbors. But what does the every cell mean? It's obviously not every cell in the universe. What do you think it is? Not enough, right? Because it's only live cells. What about those dudes that are dead and are about to come to life, maybe? What was that? Ah, every cell that gets a signal, at least one signal. Bingo, that's it. So you have a live cell here. There's a dead cell here. This says ping. This says, I got one signal. That's me. Right? Bingo, you nailed it. Every cell that gets a signal. That's correct. So in this case, we say count cells, list of cell signals. So what are we going to do right now? Return map of empty. Let me talk about this before we go any further, before we talk about it. You may look at me and say, Kash, why are you doing this, Venkat? Why are you writing a test where you don't send any data and you're simply telling me that's going to be empty? This is one of the tenets I follow in test-driven development. Ken Beck talks about this as go from 0 to 1 to many. Let me rephrase it a little bit, the way I approach it. The way I approach it is, when I'm designing a piece of code, I don't know what the method should be. What should its method be? Method name be? Raise your hand if naming methods are easy. No, right? That's one of the most difficult things we do. So I write the code. Should I call it this? I'm pairing with somebody. Hey, what do you think? Should we call it that? Hey, what should the input parameter be? What should the return type be? So my initial test helped me to tease out the skin of a function. I don't care about its guts yet. I just want to know its skin. How does it look? Then what do? I want its implementation. So here are my tests I'm going to write. The very first test I write, it defines the skin. Second test builds a little bit on the skin. But the more test I write is building the guts of the function. So I grow functions outside in, not inside out. Right? Outside in. I want to know what the function should be, and I want to know what it does internally after that. That's the reason I have these kinds of tests to begin with. So then, the next one says, I've got one signal, a cell 1 and 2, and I want you to return a map with a cell 1 and 2, containing one signal. So how do I implement that code? When I come in here, I can, kind of mess with it a little bit right now. I can say if signals dot size is equal to 0, and this is not going to sustain, right? Otherwise, return, what am I going to return? Map of signals dot get 0, comma 1. Clearly not going to sustain, but we can just start teasing it out. Is this what we really want? Yeah, that seems like it, but we need to write more generalized code. So what are we going to do next? So now we are saying, I've got a signal, 2 signals, but I want to send a map of those signals. Cell 1, 2 contains 1, cell 4, 7 contains 1. All right, now I need your help. How do I implement that function? I've got signals, and I want to return a map where the cell and the count. What function comes to mind? Don't worry about code. Don't worry about syntax. Think logic. Bingo, thank you. Right? You detach from the code, you get the answer instantaneously. What are you doing? You're grouping. Now you can go look at the JDK. Is there any function to group? Right? A lot of times that we get stuck because we are too eager. What should I type? What function should I call? Forget functions. What am I doing? I got a list. I want to group them. Oh, easy, almost. Return signals dot stream dot collect. Grouping by. What do you want to group on? Cell itself, right? So given a cell, you want to group on the cell itself. That's what you want to do, grouping by. Hey, where's grouping by coming from? From the collectors. But what do you want to store in the bucket? Don't worry about syntax, don't worry about functions. What do you want to store in the bucket? The count. The count, right? The count, number of signals, count. Counting. Make sense? Almost, right? What does the error say? Error says, hey, I want you to give me a cell and an integer, but are giving me an object and a long. Okay, a little temptation. Compiler, long. What did you just do? You said, compiler, I will do what you tell me to do. I don't care what I want. I don't care what my customer want, right? This is like, I go to the store sometime, I come home, wife is like, why'd you buy this? Oh, because they said this is on sale. Do we need it? I don't know, it was on sale, right? And we're just like, you want long, I give you long, right? How do you feel about that idea? It works, ship it, right? No. So, I don't want a long, I want an integer. I mean, you can compromise and say I want to return a long, nothing wrong with it. So then I say, all right. So back here, collecting and then. So collecting and then. Counting, comma, long, int value. Coding is like violence. If it doesn't work, do more of it. No, just kidding. But what we're saying is, oh, you will give me a long, but I don't want long, I want an integer. So you're like, okay, transform this, but before you put it into the bucket, convert the long to an integer, right? That's what you're doing. So we got a count of the signals. Let's go back here and see if that works to provide that value. And as you nicely pointed out, it's a grouping by. So far, so good, right? So here is more, and write more test, of course. So let's write this. Now, where do we go? We're almost there, right? Because we have the number of live signals. What are we going to do next? Then I say, look at this. There are some nice examples given here. You can see them as examples, or you can see them as what? Test cases. That's what I do with my users, right? My customers. Give me some examples. Why? Because I'm going to throw them in as test cases. So they're test cases. So my first test here, a dead universe stays dead. I know that's very grim. There's no life on this planet. Let's move on, right? So next generation, what does that do? The next generation function, so public, static, let's try this again, list of cell, next generation takes a list of live cells. That's what it is, right? You give me a list of live cells. That's what we're starting with. So what am I going to return from here? List of empty, right? Again, teasing out the skin. So go back and run this. What's going to happen? That's all happy. The next one, what is the next test? You know, the loner ends up being dead. This is even more grim. The last standing live cell. I don't want to be that one, right? It's like, oh my gosh, there's no hope here. So that's going to pass as well. Then what are we going to do? The next test says, universe with a faraway life cell ends up dead as well. Because these two are so apart from each other. No hope of life, right? Then what do we have here? Block stays as block. Aha, now we got some work to do. So we send a block. Remember, this is the block, right? The block stays as a block. That's what this says. So we send a block, we get back a block. How do we implement that one here? Any thoughts? We got a collection of these cells. We got the signals. So we can call the count signals, and that gives us the count. Then we can take the set, loop through, and for everything in the set, the key, you can pass it to the first function we wrote, and if it comes back alive, you return it, filter, otherwise ignore it. So a bunch of stream, map, filter, collect to a list, return. I'll leave that last step for you to play with and see how you can do it. And then once you finish it, you can then try a couple of more, a horizontal and vertical, which is these two guys. And that'll just work once you have that last step working. And that's a transformation, right? No mutation. So you can think about this to model it in a completely functional style. And it just requires a rethinking, right? It's not hard, but it's different. And it takes a bit of an effort to find it. My recommendation is, if you are serious about this is some of the really good ways to learn. Sit down on a Saturday morning, and even to make it even sweeter, invite a friend of yours and say, let's pair and work on it. And implement this test-driven from beginning to end, knowing that you can always get the source code from my website, right? So what do you have to lose? Absolutely nothing other than an amazing Saturday that you're wasted your life on that code. But that's what I do. I would sit in an airplane, my 16-hour. I do a lot of these coding on flights. This is much better than in-flight entertainment. And you can play with that, right? So that becomes a lot easier to play with and see how it works. So give it a try. You'll find it interesting to see how you can solve it. Now that you know some approaches you can take, you can try that. That's all I have. Thank you.